topic of this problem is operational amplifiers, and we're going to work with non-inverting amplifiers. The problem is to find V out in terms of the input voltages for the circuit shown below. So we have a circuit that has an op-amp in it. It has two resistors, an R sub 1, which is tied to the inverting input of the op-amp, and also an R sub F, which is the feedback resistor that feedbacks the voltage from the output to the input of the op-amp. We also have an input voltage. In our case, our input voltage is V sub 1, which is tied to the non-inverting input of our op-amp. And so what we're going to do is we're going to find V out in terms of V sub 1 for this problem. And so we have to use a few properties of the op-amp in order to solve this problem. Whenever we're working op-amp problems, we always want to understand what the properties of the op-amp are. And so if we draw a general op-amp symbol, and we also typically draw ground into that op-amp as well. We can draw it on our circuit as well. There's some current, I minus, which is the inverting input current. There's a current I plus, which is the non-inverting input current. There's also a voltage associated with the non-inverting input, V plus, and with the inverting input, V minus. And what we know about op-amps and ideal op-amps is that I minus, so the current flowing into the inverting input of the op-amp, is equal to the current that flows into the non-inverting input of the op-amp, and that they're both equal to 0. In other words, there's no current that flows into an ideal op-amp. That's not true about the output of the op-amp. It can have current flow in either direction depending on the application and what's inside of this operational amplifier. The other thing that we want to always know and to work these problems with op-amps in them is we want to understand that the voltage at the inverting input is equal to the voltage at the non-inverting input. So we're going to use these two properties. They're not the only two properties of op-amps that are important, but for this class and for linear circuits, these are our two most important properties. We're going to use those to solve our problem. And we're also going to lean on some of the tools that we've already have learned from nodal analysis and mesh analysis to solve these op-amp problems. Let's take this one as an example. So we have this op-amp circuit that has a DC source tied to the non-inverting input. And what this circuit is going to do ultimately is it's going to take this input voltage and it's going to amplify it to some output voltage level. That amplification can be greater than 1, or it can be less than 1, or it can be equal to 1, depending on the op-amp and also the elements that we've used in our circuit. So let's see how that is possible. So what we're going to do is we're going to use our properties of the op-amp. And if we do that, then we know the voltage at the non-inverting input to the op-amp. It's equal to V sub 1. And if we use our second property of op-amps, we also know that the voltage at the inverting input is V sub 1 as well. So it's V sub 1 at both points. So that helps us a lot, because now we can use some of the tools that we already have in our toolbox to solve this problem. And namely, we're going to use nodal analysis at that node of the inverting input that we just assigned a voltage of V sub 1. So it's this top node in our circuit. So if we sum the currents into that node, so let's call it node 1, and we sum the voltages into that, or sum the currents into that node, so we're going to use Kirchhoff's current law and nodal analysis. Then our equation is going to be for, first of all, the current flowing from ground through R1 into that node is going to be 0 for the voltage at the ground minus V sub 1 divided by R1. We also have the current flowing through the feedback path into that node as well. It's going to be V0 minus V sub 1 divided by R sub F. And we also have this current which is flowing out of the op amp directly into that node, and we know that that current is equal to 0. I'm going to write it down, but because it is the third branch into that node, we're going to give it a value of 0 amps. And so that's equal to 0 through Kirchhoff's current law. So what that gives us is it gives us an equation with V sub 1 in it, which is our input voltage, and V out in it. And in fact, once we rewrite this equation, we can get V out in terms of V1. So let's work on this. First of all, we need a common denominator, and then we can start adding things together. So if we do that, we'd end up with a V1 times 1 over R1 plus 1 over R sub F be equal to V out divided by R sub F. So if we continue with this, we would find that V out is equal to 1 plus R sub F divided by R sub 1 times our input voltage, V sub 1. So our output voltage is a function of the input voltage. It's not negated, so it's non-inverting. It's not an inverted signal. Otherwise, we'd have a negative sign out front. And the value of the amplification factor can be controlled by the values of our feedback resistor and the values of our R sub 1, which is attached to the inverting terminal of our op amp. So this is the example of a non-inverting amplifier. It's one of the basic op amp configurations for op amp circuits.